Hi, welcome to Lecture 11 of ECE 113. We're going to be talking about impedance matching. So why do we need to match impedances? The goal is that we must be able to transfer the maximum power from uh, your source impedance or your source right here to the load impedance. Basically, we want to maximize the power transfer between your source and your load. So why do that? For receivers, we want it to be very sensitive. So if the source and loads are not matched, then your signal will undergo unnecessary losses because of mismatch. And since the signals are inherently weak, you may not be able to detect it at all. For transmitters, you may not want unwanted reflections that will go back to your source, and maybe it could even destroy your source because this reflected power right here is added power that will be absorbed by your voltage source. Okay? And this is true especially for high power signals. So the maximum power transfer occurs not just for RF circuits but for circuits in general if your load resistance is equal to the conjugate of your source impedance. So your load impedance is equal to the conjugate of your load or your source impedance. So this will result into this canceling out with this, and your circuit will just be simply uh, purely resistive with resistances that are equal, which is needed for maximum power transfer. Just some notes. The quantity XL equals negative XS is only valid at one frequency. Okay, it's only valid at one frequency, the resonant frequency. At resonance, your maximum power transfer occurs with 50% efficiency. Since the resistances are balanced, your efficiency is at 50%. Half of the power goes to the load, half of the power is absorbed by the source resistance. At frequencies other than the resonance, the match will become progressively worse as we go further away from the resonant frequency. So, why match again? Uh, Impedance match condition should always be achieved for our communication circuits for maximum power transfer. We want to be able to have reliable transmitters and receivers. We don't want our transmitters to be destroyed because of mismatch. So we will discuss several methods to match our RF circuits. So there are three methods that be numerical analysis, that would be using circuits, hand calculating them to get your match. You can use graphical analysis, the use of Smith chart, and some software-defined tools. Okay, and there are infinitely many ways to do impedance matching. So for example, let's look at what we call the L matching network. So the L matching network is just something like this. So what's this again? It looks like a low pass filter. But how does it work? So an L matching network looks like this. You have a shunt impedance and a series impedance. Right? So shunt impedance and series impedance will transform this load resistance into another value, and it should be equal in magnitude to your source resistance right here. So these two should be equal. Okay, and then any reactance should be cancelled out by an equal and opposite reactance, so that at resonance they will just cancel each other out, and you'll be left with equal resistances that share the power from the source right here. Right? So that is your L matching network. Your L matching network could also work like this, so in the reverse direction. So let's say this disappears. Your capacitor could also be right here, and that's still an L matching network. Okay, so for example, let's look at this circuit. Using the shunt capacitance with this load resistance, your parallel resistance or the parallel circuit becomes equal to this 100 minus J 300 ohms. So this 100 is matched to the 100 ohms source resistance, and the 300 ohm reactance uh, of your inductor will cancel out the effect of the capacitor, and you're only left with, since this is a series LC, becomes short circuit, you're only left with your 100 ohms connected to your source resistance. So now your network is at maximum power transfer. Okay. So your source impedance sees a load of 100 ohms, and now your uh, excuse me, your network is at maximum power transfer. If there was no matching network use, there is a loss of due to mismatch of around 4.8 decibels, and that's actually very large. Okay, less than half of the power that you're transmitting is being received by the load. Okay. So how does matching network accomplish this? So your shunt element will transform large resistances to smaller values. Since since it is shunt element, so the properties of shunt circuits or parallel elements would have their resistance would be less than what is less than the minimum or less than the smallest resistance. Your series element will cancel out any impedance or reactance left in the shunt element. So recall the shunt to series transformation. So we've already discussed this when we were discussing resonance circuits. We can convert this series elements right here to shunt elements, okay, and vice versa using the different formulas. Okay, so basically you will need to define the quality factor of your circuit. Your series quality factor is equal to XS over RS, which should also be equal to your parallel quality factor, since it's the same circuit right here. It's the same circuit. Your Q factor will also be equal. Okay, the Q factor will be equal if even if it's series or parallel. So we define it as the Q of your series or parallel components. So using this, therefore, your parallel resistance is equal to Rs times 1 plus the Q of the circuit squared, and your parallel impedance or reactance is equal to your series reactance times 1 plus Q raised to minus 2. So this is the uh, transformation using your from your shunt to series and vice versa. Okay. So since Rp is equal to Q squared plus 1 times Rs, right? The Q can now be defined as a function of your parallel resistance and your series resistance. Okay? So the L network that you will use depends on your application actually. This part of the network passes DC. This part of your quadrant blocks DC, mainly because it's series capacitor. Here it's series inductor. Therefore, it's a low pass circuit. Here, this is the high pass circuit in this region. That's why it blocks DC. So if your source resistance is less than the load resistance, you need to decrease the load resistance to match it to R sub S. Okay, so that's what is happening here. Okay, if your R sub S is greater than your R sub L, then you need to increase R sub L. Okay, you need to increase R sub L by connecting it with a series reactance first before using a shunt impedance to cancel the effect of the reactance. Okay, so that's how you determine what type of network you will use. So after identifying the conditions of match, you just need to know if you need to pass DC or you need to block the DC. Okay, for example, design a circuit to match a 100 ohm source to 1 kilo ohm load resistance at 100 megahertz. Assume that a DC voltage must also be transferred from source to load and that all elements are ideal. Okay, so RS over is less than RL, so we need a shunt element. So you connect a shunt element first to your load resistance before connecting a series element to cancel out the shunt element. So this is our matching circuit. So this one passes DC. Since it's an inductor, it will be shorted out at DC, the capacitor will be open at DC, then DC can pass through. So first, get the Q factor that will be used, that is needed. Okay, the Q factor is equal to this, okay, which is equal to the square root of your parallel resistance times your series resistance. So the Q factor is equal to 3, and that is equal to your series impedance should be equal to QS times RS, which is 300 ohms, and your parallel impedance is RP, which is 1000 divided by 3, around 333 ohms. So X sub S here, which is omega L, equal to 300 ohms. Your X sub S is equal to 477 nanohenry, and your X sub P, which is a capacitor, it's equal to 4.8 picofarads. Right. Now, what would happen if we have complex source and load impedances? How do we unify our matching network? So in these examples, we only assume that the source and load resistances are, well, resistances. So what would happen if they are complex impedances? Okay, so in practice, this is actually what happens. Your source and load impedances are both complex. So there are two basic approaches to handle them: the absorption method and resonance method. The absorption method, this is where you will absorb the effect of your stray stray reactances. They will be absorbed by the network. Your capacitor will absorb the stray capacitance present in the circuit, and your inductor will absorb the stray inductor present in the circuit. So how will that work? So let's say you have this source impedance. This is your load impedance, stray capacitance, and stray inductance. First, you ignore the effect of strays and then design your matching network. So we already designed the matching network of this circuit earlier. Okay, we have these values for your inductor and your capacitor. Okay, so to get the inductance of our matching network, since we already have a stray inductance right here, we just need to reduce the stray inductance that is present in the circuit, and we'll get the inductance for our matching network to be 277 nanohenry, and our capacitance, since it's in parallel, so we have a stray capacitance here, we just need to reduce the capacitance that we need to match the load to the source right here. So it's around 2.8 picofarad. Okay. So your complete circuit will now be this, and your matching network is equal to this value right here. Okay. So this is your absorption method. Basically, first you ignore the stray reactances, and then assume that they will be absorbed by your matching network. Okay. So that's it. That's basically the steps to the absorption method. That's how you do the absorption method. Okay. Excuse me. Next is the resonance method. Okay. There are cases when your uh, absorption method will not work. As you can see here, you will reduce the value of the strays before you get your perfect match. But what if the value of the stray reactance is very large, such that your uh, your matching network will have negative values? So absorption method will not work in this case. So the thing that you'll need to do now is the resonance method. The first step here is to resonate the stray first, resonate the stray capacitance or inductance first before you create your matching network. So for example, okay, let's say you have a stray capacitance with your resistor. So your 40 picofarad capacitance here is a stray capacitance. We want to match this uh, load to 50 ohms at 75 megahertz, and this should block DC at the output. Therefore, your matching network will have a capacitor in series, okay, and an inductor in parallel right here. Okay. So, with the resonance method, first at 75 megahertz, your 40 picofarad uh, 40 picofarad capacitance should be resonated by an inductance first at 75 megahertz, and that is 112 nanohenry. Now, since your 40 picofarad is now gone, you just match your 600 ohms to 50 ohms normally. Okay, so doing that, you get this equation right here. Your Q factor is the square root of 600 over 50 minus 1, which is 3.32. And you compute for the series reactance and the parallel reactance, you'll get these values. Excuse me. Since we're looking at a DC block, your capacitor should be in series. So this will be X sub S, and your inductance is X sub P. So solving for their respective values, your capacitance is equal to this, your inductance is equal to this. And finally, right, you just combine these two, and now you'll get your matching network, okay, that will resonate and match the 600 ohms to your 50 ohms. Okay. Just some final notes on the L matching network or two element matching. The restriction is that we cannot define the circuit Q because the circuit Q will be ultimately defined by the source resistance and the load resistance. So you do not have the freedom to specify the Q. So it becomes an issue for high Q applications. We want a high Q, but we cannot really define the Q. Or even low Q applications where you want a wideband match. So that's where our three element matching comes in. So this three element matching addresses the issue of Q flexibility. So you can use or you can design a practical circuit Q required to achieve a Q larger or smaller than what can be achieved using L network. Basically, it gives you a freedom of degree of freedom of choosing the Q that you want. For example, one type of match rather is the pi network because it looks like a pi symbol pi right here. See? Okay. So anyway, it can be described as two networks that are back to back. You can break them down like this. And there's some virtual resistance that you're matching this two excuse me, load and source resistance with. So there's a virtual resistance at the middle that you're trying to match these two together to this virtual resistance. Okay. So the design of each section of the pi network, uh, you will first need to define a virtual resistance at which you want a specified Q. Okay. So the virtual resistance is equal to the parallel resistance. Right? Oh, sorry. The virtual resistance is equal to the series resistance. Sorry, not the parallel one. Okay? And this virtual resistance needs to be smaller than both RS and RL. So why is this so? Okay? It's because if you look at the network, X, the reactances here and here, the ones that are encircled, are parallel to both RS and RL rather. So to both RS and RL, these two reactances are parallel. That means these two will have decreased resistances when we try to match it here. Therefore, this virtual resistance must be smaller than your RP and RS. So the Q of the circuit will now be defined by this equation right here. So it will be RH divided by the virtual resistance. RH here will be the largest terminating resistance. Right? And R virtual is the virtual resistance. So it's RH is either R source or R load. So you choose which one of them is larger. Okay. So first, your computation starts with the desired Q. And with that, you determine your virtual resistance. Right? But just some note that this Q is just an approximation. It's not exact, but it's close enough for most practical purposes. All right. So design a pi matching network to match a 100 ohm source to 1 kilo ohm load, and you want it to have a Q factor of 15. So first, you need to find the value of your virtual resistance and start You start with the load since the load is larger. Then your virtual resistance is equal to 4.42 ohms. So with the 4.42 ohm virtual resistance, we now solve for the 2L networks that will match both RS and RL to 4.42 ohms that is seen here at the virtual resistance side. So for the network connected to the load, still the same calculation. You need to get the parallel reactance and the series reactance. So you get these two values right here. And for your source network, first you need to get the Q of this part of the network, okay? And you'll get 4.6. Uh, Wait, this Q is different from the specified Q. So what will happen to the Q of the circuit? Well, the Q defines uh, how selective your circuit is. So it will follow the network, the part of the network with the largest Q. So if we compare the Q of 15 that we get from this part of the network and the Q of 4 that we'll get from this part of the network, if we cascade them together, then they will just form or uh, get the response with a smaller bandwidth. Right? So that's why the formula here works. Okay, so now let's use that Q to match the source resistance to the virtual load, and you'll get these two values, excuse me, for your parallel and series impedances or reactances. Okay, so just some note. So you're left to specify what type of elements you'll use. So just note that if you choose this to be a capacitor, this should be an inductor. If you choose this to be a capacitor, this should be an inductor. Right? So you have the freedom to choose, right? And you can only choose two of them at the same time. That's why you have four types of networks, as you can see here. So there are four ways we can implement the matching network. So it's for you to decide. Okay, now let's look at a T network. So a T network, well, appears to be a T. So it's similar to the pi network. It's two back-to-back L networks. If you separate the parallel elements, you'll have another virtual resistance at the middle, similar to how a pi network behaves. But in this case, our virtual is larger than both RS and RL. So it's larger because, again, this resistance is shunt to some reactances. And since it's shunt, this virtual resistance will become smaller to match with RL. So that means this virtual resistance should be larger than both of them to be able to match to both RS and RL at the same time. Okay? So the Q of the network is approximated by this equation. So you need to get the smallest resistance instead of the largest. Okay? So in pi network, we looked at the largest. In T network, we're gonna look at the smallest resistance, which is smaller. Is it RS? Is it RL? You use that to define the Q of the network. Okay? And with that, you'll just do the same steps as how you got the matching network for the pi network, apply it to the T network, and you'll get your matching network. So general steps of three-element matching. Okay? What are the RS and RL values? Is it very high? If it's very high, you use the pi network. So your virtual resistance is smaller. If it's very low, use the T network. So your virtual resistance becomes larger. Okay? With that, you just proceed with L network matching for both sides. So basically, it's just L network matching with extra steps. Okay? Or just two of them. You just need to match two of them. Okay? More hassle, but at least you get choose your quality factor. Okay? And with that, you will now compute for the capacitance, your inductance, whatever you want to, how you will combine this network right here. Okay? So, pi and T matching networks are usually used for narrow bandwidth. So, what if we want to have a low bandwidth application? Sorry, high bandwidth application, low Q. Okay? This can be achieved by connecting L networks back to back. So basically, since your L matching network provides a small queue, if we separate the L matching networks as such, we make two matching networks right here. So we create a virtual resistance. Because of these two matching networks, your uh, bandwidth, okay, the maximum bandwidth, the one with the lowest Q, can be achieved. Okay, so you can actually reduce your uh, quality factor because of this. Again, because the L network right here reduces or restricts the queue of the restricts the queue of the design of your matching network. So if you create a series of L matching networks right here, you will reduce your queue to the point that uh, you'll have a low bandwidth application, or sorry, wide bandwidth application. Basically, you will be able to match RS to a larger range of load resistances. Okay, so that is basically if the end of matching networks. Okay, so that's it. If you want more bandwidth, just increase the number of L networks. And that's the end of lecture 9. Right. Just to summarize, we have two uh, L two ways to match our circuits, our source and load. You have your L two-element matching network, and you have your pi and T, which are three-element matching networks. Right? So it depends on your application. If you won't bother with the Q of your circuit, use L. If you need to specify a narrow Q, use a pi and T. If you want a uh, wide bandwidth or low Q, use a successive L network, and so on and so forth. So that's the end of this lecture. That's how we do impedance matching. If you have any questions or comments, if you do need any clarifications from this lecture, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting. Bye.